Hydropower is one of the oldest sources of energy. Its use goes back to 2000 years ago when Greeks used the water wheel for grinding wheat into flour. Our nation's first industrial use of hydropower goes back to 1880 when for the first time the water turbine were used, to turn on a few lights in the Grand Rapids, Michigan. In this section, we talk about the various aspects of the water. It's used to produce electricity through the traditional dams, but we also can produce electricity through the waves, through using the tidal energy, and also using the chemical gradients and thermal gradient in the ocean's water. Basically, water energy is in the form of mechanical energy. It can be due to the gravity, which is the power come from the dams and the tides, or due to the waves, motion of the waves, which depending on whether they're surface waves or the underwater currents, then they have different amount of mechanical energies. This is the simple machine, water wheels, that the water falls on it and it will turn a wheel, and the wheel is used, to lift the weight. That weight could be the weight of the water pulled out of the well, or it could be used, to maybe turn another stone and grind the flour. Two medieval varieties of water wheels are undershot and the overshot wheels. Undershot water wheels refer to paddle wheel fixed to the bank of the river or hung from an overhead bridge. It is turned by the impulse of the water current. Overshots work by bringing a stream of water through a pipe or canal and putting it onto the wheel from above. Somewhere between the undershot and overshot, we can also have breastshoot that pretty much is at the same level as the flow of the water. These are two examples. The diagram at the right is a overshot and water poured from the top, and the diagram to the left is the undershot, and as you can see, the flow of the water will turn the water wheel. Hydroelectric plants range in scale from large falling water plants used in developed nations to small river runoff plants with no dams or water storage, used for rural electrification in less developed countries. The potential for further expansion of hydroelectric plants for the most of the industrial countries is rather limited. They have already built dams wherever they could. But in the developing countries, especially in Asia and Africa, very little has been exploited already so far, and so there's a lot of potential for developing a small hydro project. This table gives the largest hydroelectric plants in the world. The largest one is the Three Gorges in China. As you can see, the height of the head is 185 meters of the drop, and it has a very large flow rate, about 12,000 cubic meter per second, producing about 22.4 gigawatt of electricity, and on the average every year can produce 100 terawatt hour of energy. The second is the Itaipu, which is in the border of the Brazil, Paraguay, and very close, to Argentina. And this one has a lower head, and the total power is about slightly less than the Three Gorges. Other power plants are in Venezuela. The USA is in the Grand Coulee in Washington, and that one is only about 1/5 as large as the Three Gorges. This is the picture of the Three Gorges plant, which is installed on the Yangtze River with a production capacity of 22,400 megawatt or 22.4 gigawatt. This is the Iguazu Falls power plant. This is the one that we visited with the students on a study abroad program. The diagram shows is basically the shaft. One end of that is a water wheel, which is inside the water, and the other end of the shaft, it goes and turns a generator which produces electricity. The hydroelectric plants is basically concentrated in only 5 states. Washington state, Oregon, California are the the 3 largest one, but there's also some water project in New York and Alabama. There are many different of hydroelectric plant types. That depends on how much flow we have and what is the height of the drop of the water. They could be called impounded plants. That is like a traditional dams. The water is pounded behind the dam and it falls, to produce electricity. The other ones are the pumped storage plants, and then there's a run of the river plants. Impound plants, as I mentioned, is a very traditional type. It's basically a water which is stored behind the dam, and through a penstock the water flows, and the kinetic energy of the water is used to turn a turbine, and turbine is connected to a generator which produces electricity. The impounds, the main problem with that is that the level of the water which is available changes during the summer and winter, and so that will cause some variation in the power during this season. Also, to build a dam, some natural flow of the river has to be interrupted, which can also interrupt the marine transportation of the not only fish but also ships and boats. It does affect the water quality somewhat because of the residue and silt which is sitting stationary in the upstream, and the silt which is flowing downstream of the dam. It may cause the flood downstream if the dam breaks, and upstream as there's overflow of the water. Because of that, population can be displaced, as it was shown in the 3 gorges. 1.5 million population had to be displaced because of the construction. The economics of the dam, of course, is very important, and that depends, the cost of construction of the dam. Initial construction is a major part of the construction, but the operating costs and transmission costs is relatively small. On the average, every hydroelectric project costs about $1,000 to $1,500 per every kilowatt of power generated, but the price goes high as the size of the project becomes smaller. The pumped storage plants means that you are storing the water to be used at the time that you need more power. The diagram at the right shows a traditional steam plants which could operate on the coal or nuclear, but this at night it can have an overcapacity. So some of this power goes to the consumer, but there's a surplus power. What to do with the surplus power is that we can use this power to run a pump. What the pump does, pull off the water from a low reservoir and pump it to a higher reservoir. In the morning, when the demand rises and the power to consumer is not sufficient, the plant cannot provide all the power, we need additional power. Then we can turn the pump backward, run it as a generator, and the water will flow back from the elevated reservoir to a lower level reservoir, producing additional power.